Classwork 1, Energy and Heat Flow. So for this first question, we are looking to calculate the change in internal energy. A system is undergoing an endothermic process. So because this process is endothermic, Q, which is the symbol for heat, is going to be positive. It also says that 1.4 kilojoules of work is done on the system. So if work is done on the system, it's going to be a positive value. Think of work as just another form of energy. So if work is being done on the system, energy is going into the system. It's sort of like it's an endothermic process. So I just need to take these two numbers and combine them, and I get 17 kilojoules. Here's another practice problem that's similar, along with the answer. Question 2 here, we want to calculate the work associated with the expansion of a gas from 46 to 64 liters at a constant pressure of 15 atmospheres. So we're going to use this equation here. Work is equal to negative P delta V. So pressure times the change in volume. So my pressure here is 15 atm, and my volume change is going to be 18 liters. So when we multiply these together, we get negative 270 liter atm. So this is kind of a funky unit, but it is the correct answer here. This could be converted into joules. And the reason this is negative is because the gas has to do work. If it's pushing against the atmosphere, the gas is doing work here, so we have a negative value. Here is a similar practice problem along with the answer. So in this question, the internal energy of a system increases by 300 joules while 75 joules of expansion work is done. So how much heat is transferred and in which direction? So we know that the change is going to be 300 joules, and we know that 75 joules of expansion work is done. So since the system is doing work, it's going to be negative here. So when we combine these, we're going to solve for Q, and we get 375. So the fact that this is a positive number tells us that this process is endothermic, so energy is being transferred into the system. Here's a similar practice problem along with the answer. This question involves a little bit of stoichiometry. So when 1 mole of methane is burned at constant pressure, 890 kilojoules of energy is released as heat. So what would be the change in enthalpy, the change in heat content, if 5.8 grams of methane are burned? So here is the combustion of methane here. So combustion is a common reaction type where you have a hydrocarbon like methane reacting with oxygen gas. And this will produce carbon dioxide, water, as well as some heat. And the problem tells us that for every 1 mole of methane, we're going to produce 890 kilojoules of heat. So 890 is going to be a product here, and this process is exothermic. And that matches what we know about something burning. It's going to feel hot because it's giving off heat. So I'm going to take that 5.8 grams of methane and convert it into moles. And I know that for each mole of methane, I'm going to give off 890 kilojoules. So if I have 5.8 grams, that's about 1/3 of a mole. I'm going to have about 1/3 of 890. So we get 320 kilojoules here. Here's a similar practice problem along with the answer. Okay, so in this question, we have two solutions that are being mixed together, and they're starting at initial temperature of 25, and then when they're mixed together, the temperature goes up by a little bit here, about 3.1 degrees. So this tells us that the reaction that's happening inside the solution is giving off heat. It's exothermic, and the water is absorbing that heat and increasing in temperature. So if we can figure out what quantity of heat is transferred to the water, we can figure out how much heat was given off by the reaction. So we're going to need to know the specific heat of solution. Also, it's going to be helpful to know the density, just because that's a convenient way to convert from milliliters into grams. And these are the same constants, the same values that we would have for water, and that's because these are considered dilute solutions. So first, I'm going to use my Q equals mc delta T, and at constant pressure, the change in enthalpy is the same as the heat change. This is convenient because most of the chemistry that we do is under the constant pressure of the atmosphere. So first I'm going to figure out the mass of my solution here. So we have 2 liters total whenever we combine the solution together. And I just converted that from liters to milliliters and then milliliters into grams. So this is just telling me that I have about 2,000 grams of solution total here. And notice that this is written in scientific notation because this number needs 3 sig figs. And the only way to write 2,000 with 3 sig figs is to write it in scientific notation. Here's my delta T. So we said it went up by 3.1 degrees Celsius. So we know the mass, we know the delta T, we know the C, we can calculate Q. So this is going to give us 26 kilojoules here. So the water temperature increases, which means the reaction is exothermic. So Q is going to be equal to negative 26 kilojoules. So we do have to apply some common sense here. Remember, we're measuring the temperature change of the water. So if the water is endothermic, if the water temperature goes up, it's because the reaction is exothermic and is releasing that heat into the water. Here is a sample problem that is similar along with the answer. So we want to figure out if these processes are endo or exothermic. So in A, we have a ionic solid being dissolved in water, and the solution gets colder. So that means that the dissolving process must be absorbing heat away from the solution, away from the water. So then the dissolving must be endothermic. The water lost heat because that process of dissolving absorbed heat. Water condensing on a cold pipe. So this would be water going from a gaseous state into a liquid state. So this would be exothermic because the water needs to lose heat in order to condense. So from the perspective of the water, this is exothermic. From the perspective of the cold pipe, we could say that it's endothermic because the cold pipe is absorbing heat away from water vapor in the air. So a lot of these depend on how you want to define your system. In this one, we have carbon dioxide gas going to solid. So we're going to have to lose heat to do that. So that's going to be exothermic. And for the next one, we're going from molecular fluorine into ionic fluoride. So we have a gas that's being ionized here. So in order to ionize a gas, you have to put a bunch of energy in. So this is going to be endothermic. So energy needs to go in to break that bond between those two fluorine atoms. Here is an extra practice problem along with the answers. In question 7, we need to calculate the calorimeter constant. So the way that we do this is we mix a known temperature and volume or quantity of water in a calorimeter, and we measure how much the temperature of the water changes. So we can calculate what that's supposed to be, but we always find that it's a little bit less, and that's because some of the heat is absorbed by the calorimeter. So if we know the actual heat change for the water, and we can work backwards then to calculate how much heat is absorbed by the calorimeter itself. And that's important because that's a correction factor that we can use to really improve our calorimetry. So first, the hot water is going to lose heat. So the mass of the hot water is going to be 40 grams. The density of water is 1 gram per milliliter. And I'm going to multiply this by C and delta T. So the final temperature of the solution is 40. So we're going from 60 down to 40, which is a negative 20 delta T. So this is the amount of heat that was lost by the hot water. Now we can calculate how much heat was gained by the cold water. And the difference between those two numbers is going to give us what the calorimeter absorbed. So the cold water has a mass of 40 grams also. There's the specific heat. And then the temperature change, we're going from 25 up to 40. So that's going to be a delta T of positive 15. So we see these two numbers are different because some of that heat that was lost by the hot water, some of it went to the cold water, and then a little bit of it went to the calorimeter as well. So the difference between these two numbers is 836.8 joules. Now the calorimeter constant has units of joules per degree, so either degree Kelvin or degree Celsius. So we want to take this amount of energy that was absorbed by the calorimeter and divide it by the delta T of the calorimeter. And so the delta T for the calorimeter then is going to be the same as the cold water because that's what started in the calorimeter, where the calorimeter is going to be at the same temperature as the solution that was inside of it. So my delta T here is going to be that positive 15. So this gives me this nice little correction factor that I can use anytime that I use this calorimeter. Here is an extra practice problem along with the solution. Okay, so in question 8, we're using that same calorimeter that we just calculated the calorimeter constant for. So we're going to burn some vanillin in the calorimeter and measure how much the water inside changes in temperature. And based on this, we can calculate how much energy was absorbed by the calorimeter as well as by the water, and that total will give me the amount of energy released during this combustion. So the energy of combustion is going to be equal to the heat absorbed by the water as well as the heat absorbed by the calorimeter. So I'm going to calculate this just using Q equals mc delta T because I know all those variables for the water. And then I'm just going to do my calorimeter constant times my delta T because that's going to give me joules. So I can combine these two and get the energy of combustion. So the total heat that was released was this number here. Now we want to know the energy of combustion per mole of vanillin. The thing is, we didn't combust a mole of vanillin. We only combusted 1.013 grams of vanillin. So we got to figure out how many moles that is and then divide our joules so that we'll get energy per mole. So here I am just converting my grams of vanillin into moles. And then I'm taking my answer from the previous question, or the previous slide rather, and I'm dividing that by the number of moles here. And then I'm just doing a little bit of conversions here. So I changed my joules into kilojoules so I could report my answer in kilojoules per mole. And this is going to require 3 sig figs for my answer because my measurement of temperature was only 3 sig figs. Here is a similar practice problem. In question 9 here, we have 25 grams of water that's being converted from 90 degrees to 110 degrees Celsius. So we're going to need to calculate using this heating curve. So on the heating curve, during the flat segments, during the plateaus, we have a phase change that's going on. So here, energy is still being added, we're still heating, but instead of changing the temperature, that energy is being used to overcome those intermolecular attractions and cause our phase change. So we start at 90, and from 90 to 100, the water is liquid, and it's just going to be the heat absorbed by the water as it goes from 90 to 100 degrees Celsius. The next segment here is where we have boiling occurring. So the boiling point of water is 100 degrees Celsius. So this is going to depend on how much energy it takes per mole to boil water. Then my last little segment here is just the steam being heated from 100 to 110 degrees Celsius. So we're going to calculate heat for each of these segments, and we're going to do it a little bit differently for the phase changes than we do for the places where we have a delta T. Because in part 1, we have a delta T here, which means that we can use Q equals MC delta T. So if I just multiply the mass of water times the specific heat times the temperature change of the water, that gives me the amount of heat here. Now in the next step, we're going to use a constant that's called heat of vaporization. So heat of vaporization applies for boiling and condensing. You just apply a positive sign or a negative sign depending on which phase change is undergoing. And then we also have the heat of fusion here. So heat of vaporization and heat of fusion give us the energy change required per mole to cause their respective phase changes. So vaporization is for boiling and condensing. Fusing is for melting and freezing. So I'm going to multiply the moles of water by the heat of vaporization here. So I'm just converting my 25 grams of water into moles of water and then multiplying that by my heat of vaporization. So once we get our answer here, we get 56.57 kilojoules. Notice that in part 1, our units are joules. So before we combine these numbers, we're going to need to do a little bit of conversion there to make them the same units. Now in part 3, we have a delta T again. So we can use Q equals MC delta T. And we get 499 joules here. Notice that I use the specific heat for steam because the specific heat of water is different for steam versus liquid versus ice. So in part 1, because we were still in the liquid phase, I used the specific heat for liquid water. So now I just need to take all of these values and get a total. So I just converted my joules into kilojoules by dividing by 1,000. And when I combine this together and round for sig figs, I get 58 kilojoules. Here is a similar practice problem. This one will take you through both phase changes.